I'm Ronja. I'm in the start of my third year of my PhD now, and I will present part of my PhD project today, which is on subject mapping and how that can be implemented in ice modeling. So I'm coming from the ice modeling side, and I'm working with a parallel ice sheet modelism in order to simulate the dynamics of the Antarctic ice sheet. And if you want to do that, it's super important to get the boundary conditions right, especially at the ice-ocean interface. Because we know from observations that enhanced subject mapping affects the dynamics also of the grounded ice, and it's actually the main reason for the current mass loss we're seeing in Antarctica. So we know that subject mapping is super important, and the way it's usually treated in standalone ice sheet modeling is to use a so-called depth-dependent parameterization. That means that the med rate is basically computed as a function of the local depths of the ice shelf base. So med rate depends on the depth of the base and also of the temperature and salinity of the ambient ocean, which is of course very hard to assess for a large scale ice shelf cavity. So in order, so the simple parameterizations are usually used, but we know from observations that med rate pairs are way more complex. And in order to catch that, one could say now, okay, let's go the whole way. And we couple an ice sheet model to an ocean model. And then we have the whole physics included in the system, and that's, of course, will yield the most realistic med rate pattern. But if you want to do long-term simulations, for example, of glacial cycles, this is computationally too expensive. So I want to present today another first-order approach in order to compute med rates in ice sheet modeling. And the idea, we're currently working on that to implement it in the parallel ice sheet model, and the idea is that in every ice shelf cavity there's a vertical overturning circulation, and we model that with a box model. So we have the deep water, or the water on the continental shelf, which is in front of the ice shelf, so we have boundary conditions there which enter the ice shelf, and when the water reaches the ice shelf base, it's melting the ice, so we have freshwater influx, which makes the water buoyant and rise along the ice shelf base. And we split that base into several boxes in order to account for different magnitudes of med rates there. And then what we get for Antarctica, or how these boxes look like in Antarctica, is this. So we use 3 to 4 boxes depending on the ice shelves, and we compute them adaptively to the geometry, so they can follow the geometry of the ice shelf strings or its paths. And the boxes are these tube-like features you see. So in order to account for very different boundary conditions in Antarctica, we split it into 20 regions, and we solve basically one box model for each of these regions. As a boundary condition, we use temperature and salinity at depths on the continental shelf. And this can be observational data, or it can be data from ocean models. And the box model also has 2 parameters. And the first parameter is linked to the overturning. And the overturning is supposed to be driven by the density difference between the water in the ocean in box 0 and the water near the grounding line in box 1. The second parameter is related to the melting. It's a heat exchange coefficient. And we use the same 2 parameters for the entire Antarctica, so we don't tune to the ice shelf specifically. And then we can see this med rate pattern for entire Antarctica. So we can see that we can span a wide range of orders of magnitudes of med rates from 7 centimeters per year in Fichneroni to 50 meters per year for Pine Island mean med rates. Zooming into Fichneroni, you see that the highest med rates occur near the grounding ice, and then towards the ice shelf front they decrease, and there's also even refreezing occurring towards the ice shelf front. And we see the same pattern for Amory ice shelf, also like highest med rates near the grounding line and then refreezing towards the front. And also the mean med rate of 60 centimeters per year fits quite well with the observed ranges. So I hope you enjoyed the talk, thanks, and if you're interested, come to see me at my poster later on.